week will be useful for you. I think this is the first step in order to find a common research. Yeah, we already find with Harshit because I follow his presentation. Very interesting, focus on mechanical properties, tensile strengths, and impact test. But as my opinion, we can carry on together, yeah, in order to develop the research on thermal properties. I mean, what happened on DAC test, what happened on the dynamic mechanical analysis, and so on. Because, you know, it's important to study these properties because actually the DAC analysis show us if the material is stable up or not and which is the temperature range, yeah, for the material. So this is also quite important. Also, I talked with Harshit about the possibility to have a common research, I mean, to replace PLA's biodegradable material as a base material, yeah? But we can use our material, biodegradable material, in order to make the reinforcement with copper particle and so on, and to study more properties without tensile strengths. Because in case of particle reinforcement, we cannot talk about the increases, yeah, of the tensile strengths. So we can study another properties, yeah, and to check, yeah, how can we do in order to avoid the agglomeration, the particle, yeah? I mean, with the other words, to have the uniform distribution of the particle inside of the sample. So I think this is quite important, and because Harshit, it's, let's say, my best friend from India, for sure we can carry on together the research. So my lecture, my first lecture for today will be focused on biodegradable material. I'd like to talk here about the liquid wood and some results that we got using the injection molding technology and of course using this material. So liquid wood, it's a brand, yeah, I mean the intellectual property belongs to the Fraunhofer Institute in Germany, and the industrial property belongs to the Technaro company in Germany. As I mentioned, I think yesterday, of course, yeah, I have one, let's say, keynote speaker from Fraunhofer Institute during our tech conference, yeah, which make a very, very interesting presentation on biomaterials. So you can see here there are three main types of liquid wood. I mean arboform, arbofill, and arboblend. There are several types for each liquid wood. Yeah, you will see in the technical literature arboform V3 nature, arboform FV nature, and so on. So many types of each liquid wood types. Also the arbofill, you can find arbofill fichte, you can find another types. So our research will focus on arboform V3 nature, on arbofill fichte, and arboblend V2 nature. Okay? Of course, for arboblend, there are also several types of this material. So, in case of arboform, these granules, you can see over there, made from lignocellulosic fibers, natural polymers, natural resins, and I put here some example. Arbofill is made from petrochemical polymers like polypropylene, polyethylene, reinforced with natural fibers like hemp, flax, or wood. And the last one, arboblend, it's up to the application. Okay, the arboblend contains different biopolymers. You can see polyestyrene, lignin, cellulose, organic additive, natural resin or wax, and natural reinforcing fibers. So you can ask me, which is the biodegradation rate, okay? We'll see a little bit later, okay? So some advantage of this biodegradable material. In case of arboform, can be 100% renewable resources without any synthetic plastics. Actually, the arbophore material has the 100 biodegradation rate during 120 days. You will see a little bit later, I mean on the next slide. High impact strength, processing with conventional machinery and equipment. Yeah, all of liquid types we can process using the, let's say, usually equipment for injection molding. Arbophile material, nice wood-like appearance. This is quite important. Take into account the surface quality. High stiffness, fewer, less pronounced sink marks. Also competitive pricing compared with the conventional plastics. Competitive pricing, but compared with the plastic materials, of course, the biodegradable material, of course, have a little bit higher plastic price because the biomaterials are now on the, let's say, beginning. We can strongly say that the material on the very beginning because the research are not, let's say, on top so far because of the huge industry of the plastic material. Arbo blend, also processing with conventional machinery and equipment, high rigidity, high surface hardness, low thermal expansion, and good water resistance. One of our direction focus, I will present tomorrow, coating the granules of Arbo blend with silver nanoparticle using PVD process because was a PhD thesis on co-tutel with University Tor Vergata of Rome, Italy, and we make a research, common research, and afterwards we got the sample with the distribution, let's say uniform distribution of the silver particle inside of the sample, because the coated process was focused on the granules, not on the sample after the injection molding, okay? I made a presentation last year on international conference, and I received an answer such as, which is the delamination, in case of coating of the granules with silver nanoparticle. We are not interested in delamination, because we didn't coated the sample. We coated the granules, and afterwards we put inside of the injection molding machine, and we got the final product. So let's see over there the biodegradation rate of the material. You can see that it's according to ISO standard, and the determination of the ultimate aerobic biodegradability of the plastic material is an aqueous, you can see medium method by measuring the oxygen demand in a closed respirometer. So let's see here the arbophore material, I mean LVs-free nature. You can see the yellow one, it's 100% biodegradation rate during more or less 120 days, 120 days, okay? Another type of material, the next one, compared with the cellulose, you can see 100 biodegradation rate during 120 days, more or less. The next one, Arbo blend, another type of Arbo blend with the green, has around 55 biodegradation rate, but a little bit period of time increases, I mean 140 days. And another one, blue one, Arbo blend V2 nature, the material that I used, around 45 degradation rate during 140 days. So this is quite good, Even if we are talking about the 45%, even if we are talking about 55%, it's okay. Also, the company from Germany mentioned that we can reuse the material up to 10 times, without changing the mechanical properties, thermal properties, structural, and so on. I didn't make, the research so far concerning, let's say, the how many times we can use the material without changing the properties, but we will see later a DSC analysis, I mean for the granules and for sample, have the same shapes. So show us that we can reuse the material, But how many times? We didn't. But of course, the research, from Germany, from Hofer, are very good one, and for sure we can reuse many times the material without changing the properties. We can ask which are the main applications. I put over there, for instance, only some examples, because there are many. Yeah? Please think about the automotive industry. Yeah? Inside of our car, up to the market, let's say, there are a lot of plastic parts inside. Yeah? So we can replace it. You will see one example, maybe tomorrow, yeah, that we started, let's say, to make a proposal, yeah, in order to replace some plastic materials inside of our cars. So you can see over there that all the material that I mentioned so far, we can use in furniture industry. Okay, doesn't matter handles, fitting, front panel, chairs, construction, slab material, junction, toys industry. Yeah, I think it's important, the toy industry, to replace the plastic material for our children, yeah, with the biodegradable material. Automotive, ornaments, switches, paneling, electrical industry, connectors, housing, and so on. Computer industry, TV, mobile phone housing. Yeah, actually, I started, I think, 9 years ago, the research on liquid wood with one Italy company in our city. Yeah, of course, I will not mention the name. Yeah, and together with them, we started to produce, as I remember well, 3 or 4 different parts for West European Union countries. Yeah, the result was okay. Was difficult at the very beginning because we didn't know the contraction coefficient of the material. Yeah, and was a little bit difficult because, you know, after 6 or 8 months, the products destroyed. Yeah, and we didn't know why, because the thermal coefficient, expanded coefficient, and so on. It's important to know beforehand, I mean before to start the production for different parts. So we mentioned that we can use the same injection molding technology. As you can see over there, it's compulsory, of course, not only for biodegradable material, but also for plastic material, to use the liquid wood pellets inside of the drying bunker before. Okay, and afterwards on the company you can use the pneumatic transfer injection machine, hopper, cylinder injection machine. Close the signal. Cylinder injection machine, mold, cooling system, transfer robot afterwards, I mean on the end of the injection molding technology, and cooling conveyor chain. So in case of biodegradable material, you know, it's important to take into account the melting temperature, yeah, of the material. So in case of liquid wood, the melting temperature for all, I think, arbofill, arboblend, and arboform, the melting temperature is between 150 up to 170. So compared with the plastic material, more than 300 Celsius, we can save a lot of energy, yeah, from this point of view. This is the reason why I will make the presentation before the experimental results that we got using the injection molding machine technology. I will make a short presentation to introduce you, I mean only the blue parts, and the day after tomorrow the other one, how to follow the design of the mold. Yeah, it's important to make an idea. Of course, some of you, I think for sure, knows, yeah, about the design step of injection molding. And I'd like to mention that it's important to start with the calculation, the weight part, choice of the injection machine, total time cycle of the injection machine, calculating the number of the mold cavities dimension according to the contraction, I mean shrinkage of the plastic material, choosing the injection system type, sizing of the runners, and gate sizing. Okay, and afterwards, the day after tomorrow, we'll carry on, yeah, only the example. So, for example, I would like to make a presentation for this type, yeah, for this type, for this part, but you can choose another one if you want, yeah, because the difference is not big, and you can use more or less the same, let's say, general sketch of the mold. So, concerning the calculation of the weight part, it's quite easy, yeah? It's density multiplied by volume. You can make the calculus for volume, you can see, and afterwards we'll have the final value for the mass. So, the choice of the injection machine. It's important to choose the injection machine, otherwise it's possible, you know, to destroy everything. I mean to have more defects during the injection of the part and so on. Because the selection of the injection molding machine is the first stage, and it is considered that the maximum volume of the injection machine to be at least 10 up to 5 times greater compared with the volume that we already calculated. Okay? So, you can see here the value, we multiply, and we obtain the final volume. We can thus choose the injection molding machine. This is the type of the injection molding machine, yeah? And afterwards to use exactly all the technological parameter of the injection molding machine that we choose. Because on general sketch, we have the mold clamp unit, we have the die and mold unit, and of course we have the injection unit of the injection molding machine. So, the characteristics of different injection molding machine, the type that we choose in this example is Z1, yeah? We have to know exactly the maximum injection volume, to know the maximum injection pressure, clamping force, it's very important, the clamping force, injection speed, also, let's say, overall dimension of the clamping plates, distance between clamping plates, maximum to minimum, ring diameter, race movable plate, maximum mold dimension, and of course the power of machine is also important. Let's go to the next. To the next is the total time of the injection cycle. Yeah, it's important to know how can we calculate the injection cycle. And first we have to take into account the empty cycle. With the minimum race of the plate 6 seconds in our case. Okay? The material speed, you can see over there, the material speed belongs to the machine, okay, for each machine. The injection time calculated, you can see the using this relation, and afterwards take into account, let's say 5 seconds compared with the injection time is similar, the pressure maintenance in the mold 5 seconds, the selected value, let's say, for the cooling time, but also we can calculate, we can make the calculus for the cooling time, okay, 20 seconds in our case. You can see that the final total time of the injection cycle is 31 seconds. So during the 31 seconds, you will see that we will get 6 parts. Yeah, we will see later. So the plasticizing capacity of the injection molding machine, it's okay. It's from technical parameters of the injection molding machine. We can multiply afterwards the mass with the correction factor. You can use also the net weight of the injected part and the correction part factor. You can see that we obtain 25s, okay? So the correction factor is 1.1, okay? So it's compulsory to make this correction, and you'll see later why we need to make the correction, because during the cooling time, we'll talk about during the pressure variation inside of the mold, yeah? Because the shrinkage of the material, the machine, send more material inside of the mold cavities, okay? So, number of the cavities, you can see the relation in order to calculate the number of the cavities, and finally, for this example, we obtain 6 cavities. What means 6 cavities? During the 31 seconds, we'll get 6 parts, okay? So we'll be design an injection mold with 6 cavities. Also, we can calculate the cavities, take into account the economical number, yeah, of the cavities. And you can see here the relation, and we have to take into account, you can see the total injection time, the salary per hour for the worker, but it's up to the countries, yeah. So we cannot, let's say, make the calculus from the economical point of view, yeah. During, let's say, our example, the calculation is made only from the technical point of view, and of course, the cavity manufacturing cost we have also to take into account. One very important step, I mean the nominal dimension and the tolerance for injected part and the cavity. It's very important to know the nominal dimension of the cavities and which are the tolerance for the cavities. Okay? So, if denote a nominal dimension of the piece with h and the tolerance with delta, of course the actual size of the piece will be h plus minus delta, okay, in case of the part. Similarly, if we will note the cavity dimension with capital H and the tolerance with capital delta, of course the actual size of the cavity will be h capital plus minus delta. So the maximum size of the part, you can see the relation, will be done with the maximum size of the cavity. Isn't it? Yeah? When contraction, I mean the shrinkage is minimum 1. And the minimum size of the part will result with the minimum size of the cavity when the shrinkage is maximum 1. We have to take into account the figure 2. Yeah, we can write the relation. It's quite easy. Yeah, it's quite simple. You can see, you know, the link between the dimension. And if we gather and decrease the equation from above, I mean declating the very small terms, I mean delta C minimum, delta C maximum, and so on, and introducing the notion of average shrinkage, you can see, average shrinkage, we can get the results, the relation to make the calculus for capital H, capital delta, and this is a condition, yeah, for the part tolerance, and use the condition in order to obtain the cavity tolerance. Okay? So the shrinkage of material also it's important to take into account, and I mentioned that we use the harsh PVC, and you can see here the shrinkage value in case of harsh PVC as material used.
So here it should be C max minus C min, or it should be plus?
Yes, we will replace. Of course, you can see in case of PVC material, okay, C minimum is 0.1, okay, the maximum one is 0.5, yeah, we make the average, okay, 0.3, okay. And afterwards, the table 4 is quite important. Why? Because, did you remember? I put the 30 millimeters as inner diameter, okay? 40 millimeters for outer diameter of the part, and 36 millimeter height of the part, okay? So, we can write for the cavities in case H1, I have the relation before, take into account the condition that the tolerance of the part must be bigger than, okay, we can adopt it, the tolerance for the part. And afterwards, we can calculate the tolerance for the cavity. So this is the important step. And you can see over there, all the calculus, it's compulsory to be done for all dimension of the part. Inner, outer, and weight of the part. Of course, it's the simple one. Yeah? In case of complex part, of course, there are more calculus to be done. Choosing the injection system type. You can see that in our case, because the part is simple one, okay, the runner is reduced to the 6 cavities. We will be selecting an injection system by distribution channel. You can see here in the figure 11, injection molding through distribution channel. I mean injected part, both, left and right. Branch runner, you can see, number 2. And main runner, number 3. And the sprue. Yeah? I mean the runner and the sprue we can reuse. We can reuse. Take into account the recommendation of the producer that we can reuse the material up to 10 times without changing the mechanical properties and so on. And about the placing the cavities inside of the injection molding in case of the runner, you can see there are many, many possibilities. Okay? It's up to us. No problem. Yeah? Only you have to create, only to put, but one condition, the injection point, it's compulsory to be symmetrical. Doesn't matter we are talking about the horizontal plane or we are talking about the vertical one. Yeah? So the injection point must be a symmetrical one. You can see during one injection point we can get, well, I think 30 or something like that here. Another runner, you can see over there. But also we have taken into account when we create, let's say, the cavity, I mean the placing cavities about the dimension of the injection molding machine. And not to lose, more material because as longer the runner is, yeah, as much it must more material we can lose during the injection molding. So we have to find, let's say, optimum from this point of view. Sizing of the runners, this is quite simple. I mean, you can use the maximum wall thickness, yeah, for the injection part. In our case, it's 5 millimeter, and afterwards you can obtain, the diameter, and the runners will be with circular section. Of course, there are different, let's say, section for the runners. Yeah, square doesn't matter, but in our case, the suitable one is circular one. And finally, you can draw, you can see the root of the runner. It's important to make the calculus for the length of the runner. We'll have here the diameter already calculated over there. And be careful here, I mean, take into account the maximum diameter, outer diameter for the cavity. And between cavities, you can see, yeah, it's compulsory to have the next rounded value of the maximum diameter of the cavity. Yeah, I mean to have 40.12, it's the recommendation to take 41 millimeters. So it's important. And afterwards you can make, let's say, all the calculus, because the length, the total length of the runner, because the runner, I will come back. Because the runner not means only this one, okay? Means also this part, okay? So we have to add more, yeah? That's why you can see the relation in order to calculate the final, let's say, length of the runner. Flow of the molded plastic injected, and of course, we can calculate also the section of the area and calculate also injection speed. We take from the parameter of injection molding machine. Gauge sizing. This is also quite simple. Technical literature make the recommendation something like that, at least, let's say, 2 millimeters. You can see also the angle and, of course, the gauge circular shape with around, in our case, 3 millimeters. Okay, I made, let's say, half of part concerning the design of the injection mold. We'll carry on afterwards. And now let's come back to the experimental results concerning the liquid wood. So the experimental results use the Taguchi methods. Yeah, doesn't matter. Nowadays there are, several different, let's say, research methods that we can use, but also Taguchi, it's a good method to take into account. You can see also the model for Taguchi and the levels value of the input parameters. I mean temperature, 2 levels, injection time, okay, cooling time, screw speed, injection pressure, and mold temperature. Take into account the recommendation from technical literature. You already know that in case of plastic materials, there are fixed temperature. Yeah, I mean, let's say for PVC, it's compulsory to have the mold temperature at 50 Celsius and so on, because otherwise it's dangerous for the mold. We can destroy everything because the temperature range, yeah, is higher in case of plastic material, but even for the biodegradable material, because we are talking here about the high productivity. Yeah, we are not making, you know, 10 parts or something like that. Yeah, we are making hundreds, and that's why the temperature increases quickly. Yeah, and very dangerous for the mold during the injection cycle time. Our research, as you can see over here, I mean the top view displaying of the active plates of the injection mold within the injection angle. So first we consider, yeah, this runner in order to obtain the sample. I mean 0 degree. We call 0 degree. But we can use also the thin film. Okay? I mean 90 degree for the injection direction. Yeah? So keep in your mind the 0 degrees, it's something like that, and thin film means the 90 degree injection molding. Let's see a little bit about the tensile stress for the materials. And the first one is focused for the arbophil material, as you can see over there, fichte, at room temperature and 60 degree. We study also the properties on higher temperature. Why? Because if we want to focus, let's say, on automotive industry, you know that during especially summertime and so on, yeah, the temperature could be higher, and it's important to see the behavior of the material, yeah, let's say on the highest temperature. So in case of arbophil material, you can see that the tensile it's around 28 megapascal with the, of course, deviation of the room temperature. And in case of the 60 degree, you can see the 13 megapascal. The next material, arboband, the tensile strength reach around 44 megapascal at room temperature, but was not possible to study this material on the 60 degree, 60 Celsius. Yeah, why do you think? Because it's a strange, yeah, of the machine which exceeded, you know, the machine range, yeah, and was not, yes, and it was not possible to obtain the results. So this is the main conclusion, okay, that we can get from the tensile strength. So for arbo blend, in case of the room temperature, the base value, as I mentioned before, 44 megapascal, and the material had a brittle behavior. We try to get, because you know, our research goals is to obtain our materials, okay? And we started to obtain, let's say, new material reinforced in this case with aramid fibers. Okay? We study also the materials reinforced with glass fiber, 5%, 10%, 50%, but no more. Because, you know, highest reinforcement percent, yeah, means, you know, more or less the base material. We cannot use, let's say, 45, 50% for the reinforcement phase, yeah, and 50% for the base material. Yeah, we can try to get more and more, I mean, better and better properties with the smallest as much possible the reinforcement percent. This is the main goal. So in case of aramid fibers, you can see at room temperature with reinforced with aramid fibers, you can see the value increase around 48 megapascal. So the results from this point of view was quite good, but you can see at room temperature at 60 degrees Celsius, the results are not okay, somewhere 4 megapascal. So we are not interested in this material or the highest temperature. Concerning the for the arboform material, concerning the tensile stress vs elongation, you can see also. So the blue one, oh, here it's black, sorry. The blue one, it's 0 degree injection molding, and the red one, it's 90 degree injection molding. Yeah, you can see the results in case of 0 degree injection molding. I mean the agglomeration of the value. This means okay, because also the deviation, yeah, are smaller. Yeah, and in another case, I mean 90 degree injection molding, you can see the value. Yeah, so this is not, let's say, a suitable injection molding direction that we can choose in order to obtain better properties. The second material, I mean arboform reinforced with aramid fibers, yeah, better results in case of 0 degree, and even we can say better results in case of 90 degree. Yeah, take into account, yeah, the first results. The main effects of the input parameter, it's easy to see. You can see the cooling time has the major role, I mean the biggest influence, of course, on the final product. And this is for base material, I mean for arboform material. And the next one, I mean the arboform material reinforced with aramid fiber, you can see that also cooling time has, let's say, major affect the properties with the melting temperature and initial parameter, because also melting temperature, as you see at the very beginning, we use 2 levels, 150, 170. So it means, yeah, that 170 Celsius can be reduced. So this is quite good, okay, from this point of view. Also, tensile strength versus elasticity modulus. You can see the results in case of arboform base material, arboform nature. Also, the tensile strength versus Young modulus in case of arboform reinforced with aramid fibers. And of course, you can see also the 0 degree injection molding could be, let's say, the better solution in order to obtain. And downstairs, I mean down the figure 10 and 11, which are the main factors with the major influence over the final properties of the product. So let's go further to study a little bit X-ray diffraction to see the results, to study the DSC analysis to present the main idea. So X-ray diffraction analysis, you can see on the literature XRD analysis, allows to what? To determine the crystallographic structure, and it works by irradiating a material with X-ray, okay? And afterwards measuring the intensities and scattering angle of the X-ray that leave the material. So this is the main idea what X-ray analysis is doing. In case of first material, I mean arbophyll fiche, you can see clear that we have a crystalline structure, because you can see over there the Miller index, okay? So the Miller value, so it's okay, it's a crystalline structure. If we are going further to the next material, I mean the ArboBlend V2 nature, you can see the structure is half and half. Yeah, I mean half crystalline structure, and the second one, I mean amorph structure. And the last material, arboform, you can see has the amorphous structure. And of course, the material does not have a complete amorphous structure presenting on the level, because it's important 15 to 13 degree a few typical phases. So this is important to establish at the very beginning, which is the structure of a material, because afterwards we need to know it, yeah, to develop, let's say, another experimental research. Micro-indentation test is also important, because you can see this research revealed following mean recovery value. In case of arbofil material over there, the value is 45 micrometers. In case of arboblend material, the value is 22 micrometers. And in case of arbofoam material, the recovery value is 17 micrometers. These recovery values are in agreement with the micro hardness and elasticity modulus. It's very important to point out this conclusion. And of course, you can see here the displacement, the recovery, micro hardness, indentation modulo, and of course, the load forces that we used during the experiment. Of course, micro-indentation test for our material, I mean reinforced with aramid fibers. You can see in this case that the recovery material for the study is 29, as against the base material, which was 70 micrometers. Yeah? And you can compare, of course, the material displacement and the others. You can see the values that we got after the micro-indentation test. We were going further, yeah, to see what happened on the nano level indentation, I mean nano test, and was a good collaboration from this point of view with Professor Esteban Breutmann from Linköping University, Sweden. Now he is working on SKF. He is one best of friend of mine, okay? And we studied together two liquid wood materials from this point of view. And now we are carrying on, more research. And from this point of view, you can see the roughness, yeah, in case of arbofoam material and arbofoam reinforced with aramid fiber, you can see the values, yeah, and the melting temperature, because we used two levels of the melting temperature, 150, 160. Yeah, you can see the lowest value, it's around, let's say, 750 nanometers, yeah, and you compare also the deviation, yeah, with the deviation of our new material reinforced with aramid fibers. Yeah, you can see the value, we can compare the value more or less. Yeah, 500, let's say 750, 500 nanometer, but we cannot compare the deviation. And afterwards, nano indentation low displacement, you can see in this figure, of course, take into account what? The injection molding angle, temperature, 90 degree, 160 degree, 0 degree, 160, 90 degree, 150 degree, and 0 degree, 150. And of course, for our material. Nano indentation hardness in Young modulus, you can see the angle, I mean 0, 0, 90, 90 for base material and reinforced material. And you can see also that in case of base material, the best results, I mean the highest hardness, nano indentation hardness, it's around 350 megapascal, and the Young modulus 5.9 gigapascal. The SPM also, imagine, it's very important because you can see the picture reveals a rough surface and there is not piled out material, okay? No piled out material, I mean without agglomeration of the material where around, you know, around the gap. So this is quite important because assures the validity of the micro hardness and Young modulus. There are, of course, technical literature relation in order to make the calculus, yeah, for I mean Oliver and Farr. We carry on also with the friction coefficient and wear, because it's important to know the tribological properties in order to use the part that we got on different industrial application. So we started for base material, 0 injection angle, 150 Celsius, I mean in this case. The second one, also for base material, but with 90 degree and 160, excuse me, also 0 degree injection angle, but the second one with 160 Celsius as melting temperature. So let's talk a little bit about this one. You can see that we used 1 Newton, 3 Newton, and 6 Newton loading force. Okay? So if you want to make a short comment about the friction coefficient variation, you can see that during 20 seconds, well, it's difficult to see over there, but I know the results, yeah? Let's see, let's have, you know, the value up to 0.35 for friction coefficient. Afterwards, up to the loading force, yeah, up to 200 seconds, yeah? I mean, the value are the same for all the loading force, and afterwards increase, not suddenly, okay, increase up to the, let's say, 0.44 during the 1000 seconds. This is also good results from the friction coefficient point of view. Look to another variation of the friction coefficient, I mean, in case when we use the 160 degree Celsius for melting temperature. Yeah, the behavior of the friction coefficient is a little bit different. Yeah, it's the same during the first 22 seconds, but afterwards, you know, a little bit different behavior. Let's say up to the 700 seconds, and afterwards, the say altogether have the same behavior. If you are going further to the next one, I mean our material reinforced with aramid fiber, you can see 0 injection angle, okay, melting temperature, 165, and of course 0 injection angle, but with the increasing melting temperature, 175. So the first one could be also let's say, the same with the base material. But something strange was happened here in case of 175 Celsius degree as melting temperature, because first one, the results for 1 Newton, you can see during 20 seconds around 0.15, yeah, increases not suddenly, yeah, up to 0.2. But when we change the loading force 3 Newton, yeah, you can see it's total behavior of the friction coefficient, yeah, and also for the 6 Newton. This was the reason why we decided to upload, I mean, with 2 Newton forces, loaded forces, to see which is the behavior between 1 Newton and 3 Newton. And that's why in this figure you can see, yeah, the second, another research with loading force 2 Newton. So this is a little bit strange, let's say, behavior of the friction coefficient. And of course, we have to make more research to find the reason why, yeah, there is a big difference between the results between 1 Newton and 3 Newton loading force. Concerning the wear tracks. So here, I mean, the results were as we expected. I mean, the wear tracks increases with the loading force. You can see, yeah, loading force 1 Newton. Yeah, this is the wear track, 3 Newton and 6 Newton. So also for our material, the wear tracks were the same. I mean, increases with the loading forces. DSC analysis, I mean differential scanning calorimetry, as you already know, is the most popular measurement technique in order to detect endothermic and exothermic transition. Yeah? So it's important to know the endothermic and exothermic transition for the material. And the first recorded thermogram for arbophil, the second for arboblend V2 nature, and the third one you can see for arboform LV3 nature. The first material, for arbophil material, you can see that arbophil, a solid state transformation, and it's thermally stable up, let's say, to the temperature around 423 Kelvin. So this is the results, it's quite good. If you are going further to the next material, I mean arboblend, even also arboform, you can see there are two peaks. I mean one endothermic and one exothermic peaks. Well, it's a little bit strange from this point of view, because usually the material has one peak. Doesn't matter if it is endothermic or exothermic peaks. But we can explain this one because of the water evaporation. Okay? We can explain this one with the water evaporation. So, as a conclusion here, the two transformations occur within the same temperature range for both analyzed sample. And of course, here you can see the summary of the data evaluation with the software, I mean Proteus software, used tangent method for critical temperature, of course, for all the material. I mean, which are the temperature on different points.
So, water evaporation will take place below 100 degrees Celsius, 340 Kelvin.
Yes, yes, could be change the temperature from this point of view. Water evaporation, because it's biodegradable material, yeah, and we have, yeah, possible inside some water, and that's why appears two peaks. Usually it's we can get only one peak.
So first peak is due to when water evaporation will start.
Yeah, yeah.
And second peak.
So appears first peak, and afterwards appears the second one. Yeah, because increases the temperature. Yeah, and of course water is in process for evaporation.
Okay, sir.
Okay.
So is there any phenomena of something like pool boiling, or that, or there is no importance to that? Different kind of boiling regimes are there.
It's not important. Yeah. So let's have a little bit details about peaks. Yeah, you can see the detail of first peak and the detail of the two peaks. I mean all the information that you need in order to have a deeply study of the peaks. Okay. So, but the important, as my point of view here, is the DSC analysis, of course, as a function of temperature, for what? For the sample that we got and for the granule. Okay? So the blue one is for the granule and the red one is for the sample. So you can see over there more or less the same behavior. That's why I mentioned at the very beginning that this is the first conclusion that means we can reuse the material from this point of view without changing, let's say, the thermal behavior of the material. How many times? We didn't study so far, but we can do it. Yeah, we can do it. But in the same time, we have to, it's compulsory to have a good connection in case of the reusing of material with the other mechanical properties. Okay? So we are interested, of course, in mechanical properties. Yeah? And we have two connections, because let's say up to 5 times reuse of the material could be destroyed, yeah, the mechanical properties. And of course we will stop. We will not carry on, yeah, to use the material. So this is important, let's say, conclusion concerning the DSC analysis for the sample and for the granules. Also, for all experimental research, we done the DMA analysis. I mean dynamic mechanical analysis. Because you can see I put some conclusion here. This analysis measures stiffness, I mean storage and loss modulus, and damping, tan delta. Okay? So you can see the first curve, it's for tan delta. Okay? Okay? And the second one, storage modulo, and the third one, crystallization curve. This is also very important, and you can see here some information about the equipment that we use. But if you want to read more about the method, the results, I mean the detailed results. Of course, you can check our papers, my papers, yeah, on different journals, and to see over there, yeah, I mean the deeply comments about the results. So this is the important, because the DME analysis show us what? The glass transition temperature that in this case appear as 61 Celsius degree. Okay? In case of our material reinforced with aramid fiber, you can see the behavior more or less are the same. I mean the blue one is arbophore reinforced with aramid fibers, and red one is the base material. Okay? So the behavior is the same. This is quite good from our point of view, because from the DMA analysis we have, let's say, the same results, the same behavior of the dumping and the yeah, modulus, yeah, for the material reinforced with aramid fiber.
So what is glass transition temperature?
What?
Glass transition temperature.
Yeah, glass transition temperature appear at 61 Celsius. This is important.
What is glass transition temperature?
Glass transition temperature. Glass transition. What can I explain more? Glass transition. Yeah, yeah, of course, glass transition, okay? 61 Celsius. This is important, yeah, as a main conclusion. Scratch analysis. You can see the scratch analysis in our case we done, and I put here only, yeah, few results. I mean in case of test number 4 with 90-degree injection angle, you can see the deviation, yeah, the diagrams. Also, you can see the results in case of scratch zero angle injection molding. Of course, more or less, the results, let's say, will be the same. The conclusion, from east to west direction, the value of the friction are higher, yeah, compared with the north-south direction, because you know of the injection angle that we used. Surface analysis, also the surface analysis, you know, it's important, yeah, because we are talking about the quality of the surface. And you can see here the surface analysis from east-west direction, I mean the roughness, yeah. Let's say the smallest one around 0.6 micrometers, and for the north-south direction, you can see the small one roughness around, let's say, 0.4 micrometers. And of course here the major influence, let's say, parameter over the roughness is the angle injection, okay, for sure, from this point of view. And of course you can see over there that the length analyzed on x-axis was 2 millimeter, y-axis 2 micrometers, sorry. And of course the speed and some, let's say, surface images for the roughness that we make the analysis. Well, I don't know if my lecture now was enough or not, yeah, but I tried to make an idea, general idea. We are talking more, yeah, about biodegradable material on the next, let's say, lecture. Yeah. If you have questions, please.
So these tests were done at when the material was new, or were they also done at different levels of degradation? Because this
no. The scratch analysis, no, on the new material. I mean, afterwards we get the sample using injection molding, right. Not after degradation. So yeah, I saw only the biodegradation rate to see the impact, you know, with the environment. Right. Okay, because you know the bottle from plastic materials, it's needed 500 years, okay, yeah, in order to disappear, okay, yeah. So that's why I put the information over there, and keep in your mind that the biodegradation rate is not calculated on the atmosphere, okay. It's a specific I mentioned, yeah, which are the, let's say, the zone, which are the medium, yeah, for the biodegradation rate. But this is quite important.
Was it aqueous medium, water?
What?
It was in water, right? Aqueous medium.
No. I put the information at the very beginning, which is the medium, yeah, for the biodegradation. Yeah.
These are food grade materials. These arbophil and
yeah.
arbofoam. Are they food grade polymers? So even food packaging industry can use such.
Yes, yes.
That's where another space where a lot of polymer is plastics are used a lot.
Yeah, the Arbo blend and the Arbo fill has a little, polymers, because I mentioned about the lower degradation rate, 45 and 55, but Arbo form without. Yeah, lignin is highest percent, yeah, of the component inside of the Arbo form. It's 100 biodegradation material. Yeah. Now I have, with the same company in our city, yeah, let's say a possibility to make a research and to make different plates for one company on Japan. They are interested in this material, and I think they will visit us on the end of the July.
And sir, just to get an idea, how expensive are these granules as compared to
Yes,
regular
yes,
material?
it's expensive. Yeah, it's expensive as always. Yeah, the new material, new products also at the very beginning are expenses. Yeah, to make compare with the plastic material,
Yeah.
20 kilo, for instance. Yeah, when I bought it was around 250 euro. Okay, compare with the plastic material, let's say with polyamide, it's around 50, I think, euro for 20 kilo. So big difference. Yes, it's expensive, but take into account the friendly, link with the environment, and of course with our life. Yeah, I think it's okay from this point of view.
Sir, I believe this concept can be extended for life cycle analysis of the process itself, because that is very important for sustainability point of view.
Yeah,
When we say
You can extend.
biodegradability and the sustainability.
yeah, of course you
So
can
is
extend.
there any open source available literature in this area wherein this life cycle analysis is conducted for this approach? This material and this process, that is injection molding.
It's not open source.
Okay.
Okay, it's not open source, the results, but we can collaborate if you want.
Yeah, because
Of course,
when
we
it
can
is
share.
biodegradable, we can of course connect it with the sustainability part for the
Mhm.
circular economy when
Mhm.
we say.
Yeah,
right?
take into account the circular economy,
Yeah.
the biodegradable material, it's suitable from this point of view. Because, did you remember my last lecture? We have to return
Yeah,
to
of course.
Earth.
Yeah.
Many materials didn't. Okay?
Yeah, thank you.
Okay.
So what are the current application of this liquid wood, arboform and arbofill?
I mentioned, I think on the first or second, third slide, yeah, which is the main, yeah, application that we can
Those
find.
were areas right now where these are currently
Yeah,
being
are used. Yeah, of course, are used. Furniture industry, automotive industry, of course. The Ford company made the first Harshit also present 3D printing. Please remember the company for the electric car. But for not, but not from, I think, biodegradable material. Ford
Yeah.
company did it, but using the liquid wood. Yeah, but be careful about the weight
Yeah.
here. Yeah,
If it is
it's heavy. It's heavy compared with the plastic material. Yeah. Yeah, of course. Yeah. Okay. Thank you very much. Thank you.